If we continue down the column to potassium, we see that the potassium metal is also stored under mineral oil to minimize its reaction with the oxygen in the air. If we remove a piece of potassium metal, we can see that the potassium is coated over with a gray coating of the oxide. As we continue down the column, group 1 metals get softer and softer. The potassium cuts very easily. As we cut through the metal, we expose the shiny metal surface underneath. The potassium is extremely soft. We can easily flatten out the potassium metal. It has a consistency of cream cheese. The potassium is a metal and is an excellent conductor of electricity. If we add a piece of potassium metal to water, we see that it reacts much more rapidly with the water than the sodium. As you go down the column, the ionization energy decreases and the metal reactivity increases. The reaction is very exothermic, and the hydrogen that's produced ignites. We can test for the formation of potassium hydroxide by adding phenolphthalein. The solution turns red-purple due to the formation of potassium hydroxide. We'll go down the column on the periodic table in group 1 and look at sodium. Like the lithium, the sodium is stored in mineral oil to minimize reaction with the oxygen in the air. If we remove a piece of sodium metal, we notice that it's also coated over with an oxide coating. Group 1 metals become softer as you go down the column. The sodium is much easier to cut than the lithium. As we cut off the oxide layer, we can see the shiny metal underneath. It coats over very rapidly with a layer of oxide. The sodium is a metal and is an excellent conductor of electricity. If we take a piece of the sodium metal and add it to water, we notice a much more rapid reaction with the water. Like lithium, the sodium is less dense than water and floats. The metal moves across the surface, being pushed by the hydrogen gas that is produced. As you go down the column with group 1 metals, the melting point of the metal decreases. The reaction is very exothermic, which causes the sodium metal to melt. The metal contracts into a very compact spherical form. We can again test that hydrogen gas is being produced by this single displacement reaction by trapping the gas and testing its flammability. We can test for the fact that we produce sodium hydroxide by adding phenolphthalein. The phenolphthalein turns a purple-red color due to the presence of the hydroxide ions, indicating the formation of the sodium hydroxide. Group 1 metals are very reactive because they have low ionization energies. One of the ways that indicates its high reactivity is the way that we store the metals. Group 1 metals are typically stored under kerosene or mineral oil to prevent or limit their reaction with the oxygen in the air. Let's look at some of the physical properties for Group 1 metals. We'll start out with lithium. The lithium is coated at this point in time with a layer of both the oxide and the nitride, and we end up with a fairly dull gray appearance. Group 1 metals tend to be relatively soft, and we can easily cut the metal with a knife. What we can do is we can see the shiny metallic surface underneath. If we bring in a conductivity tester, we can see that the lithium is an excellent conductor of electricity. If we add a piece of lithium to the water, one of the things that we notice is the fact that the lithium floats. Group 1 metals are less dense than water. We also see that the lithium reacts very rapidly with the water. This is a single displacement reaction producing hydrogen gas and lithium hydroxide. The lithium hydroxide is very water soluble and dissolves in the water. The hydrogen gas escapes. If we trap some of the gas in a test tube, we can test that the gas is actually hydrogen by testing its flammability. We can test that lithium hydroxide has been produced by adding an acid-base indicator. If we add some phenolphthalein, phenolphthalein is colorless in acid and red-purple in base, we can tell that the solution is basic due to the formation of the lithium hydroxide. If we go across a row on the periodic table from sodium to magnesium, the ionization energy increases and the reactivity of the metal decreases. One thing that's very apparent is the difference in how we store the metals. Magnesium is not stored under kerosene or mineral oil, it's stored out in the air. And even after being stored out in the air for months, the metal still has a very shiny surface. The magnesium is an excellent conductor of electricity, as we can see using our conductivity tester. It's also a very malleable, flexible metal. If we add the magnesium metal to some water, we notice that the magnesium metal sinks. Group 2 metals are more dense than water. We also notice that there's no apparent reaction between the magnesium metal and the water. The magnesium metal has a much higher ionization energy than the sodium and therefore a lower reactivity. The magnesium will react slowly with the water at room temperature, but the reaction will increase significantly if we warm the sample. The bubbles that we see are not hydrogen gas, but steam. The solution will turn purple over a period of time as small amounts of magnesium hydroxide are produced. In order to demonstrate that we're getting a reaction, we'll add some phenolphthalein to the test tube. The solution will turn purple due to the formation of magnesium hydroxide. If we go down the column in group 2, from magnesium to calcium, we see that the calcium is also stored in the air. Instead of being a shiny metal, the calcium is coated with a layer of the metal oxide. As you go down the column in group 2, the metals tend to get harder. Calcium is malleable, but requires a great deal more force to shape it. Calcium is a metal and does conduct electricity. If we add the calcium metal to water, we get a much more rapid reaction of the calcium with the water than the magnesium. The reaction is very exothermic. This is due to the lower ionization energy of the calcium. We get a single displacement reaction producing hydrogen gas and the formation of slightly soluble calcium hydroxide. We can test for the hydrogen gas by collecting some of the hydrogen gas in a test tube and testing its flammability. We can test for the presence of calcium hydroxide by adding phenolphthalein indicator. The indicator turns purple, indicating that the solution is basic and that calcium hydroxide has been formed.